Hello, pre-calc honor students. Here we are with 17.4, continuity and one-side limits. First, the idea of continuity. Let me give you a picture so you can understand what this is all about. Visually, a function is continuous if you can draw it without picking up your pencil. So if I've got a coordinate system here, and I put a function in like a polynomial, it's continuous. And the whole idea of this idea is it continuous at a point, means that basically the limit agrees with the value of the function. So if I've got some point x equals c here, and this is f of c, that basically not only is f of c existing, the function is defined at x equals c, and not only does the limit as x approaches c of f of x exists, that is, whether I come from the left or the right, it seems to be approaching the same y value, but that we put these two ideas together, and that the limit as x goes to c of f of x equals f of c. That the limit and the value of the function agree, then it's a continuous function at that point. Now here's some properties of continuity. If I took this whole function and doubled it all, it would still be continuous. That's this first one. If you multiply by a constant, it's still going to be continuous. You can add and subtract continuous functions and get more continuous functions. Multiply them, still continues. Even divide them as long as g is not equal to 0. And take compositions. Now here's the intermediate value theorem. Let f be a continuous in the interval from a to b, and let k be any number between f of a and f of b. So if I've got some continuous function that goes from, let's say, a to b, and f of a and f of b are over here then. If I pick some k here, and k is the intermediate value, if it's in between f of a and f of b, then there must be somewhere in the function where you attain that value. Some c in the closed interval from a to b, such that f of c equals k. And this is just kind of obvious once you think about the idea of what it means to be continuous. If I'm going to be continuous, I'm going to have to connect the point a comma f of a with b comma f of b with a continuous connected set of points. So that means I am at some point, I can try and avoid k for a while, but at some point, to stay continuous, I'm going to have to connect up to f of b, and so I'm going to have to go through the value of k. So we can use the intermediate value theorem to prove that x cubed minus 5x plus 3 has a real root between 1 and 2. Well, let's look at f of 1. F of 1 is 1 cubed minus 5 times 1 plus 3, and that's equal to negative 1. F of 2 equals 2 cubed minus 5 times 2 plus 3, and that's equal to 11 minus 6 is equal to 5. No, 8 minus 10 negative 2 is equal to positive 1. Positive 1. So, k is a value in between negative 1 and 1. In this case, k equals 0 because I want to find a real root. I want to know when is f of x equal to 0. Let's look at this on the picture now. What I found here was f of 1 goes to negative 1. So there's negative 1. And f of 2 goes to positive 1. 0 is a value in between those, so I will attain that value somewhere in this interval. And it's right there. So by the intermediate value theorem, there must be a c in the interval from 1 to 2, such that f of c is equal to 0. And k equals 0 in our case over here. We could also do the same thing to show that there's a root between 0 and 1, and there's also a root between negative 3 and negative 2, because it changes sign, so it must pass through a value of 0. Now, one-sided limits are based on the idea that x approaches c from a certain direction, from values basically bigger than c. So this actually, for all epsilon greater than 0, however small there exists a delta greater than 0, such that we want to just focus on the fact of, we don't need the absolute values in there, x minus c is less than delta is greater than 0. Don't put the absolute value in there, because we're always talking about x is bigger than c, because we're looking at the limit as x approaches c from the right of f of x equals L. That's what that plus symbol means. When I look at it, it's like an exponent, but it actually means as you approach the value c from values bigger than c. And the left-handed limit, notice the switching of this now, c is less than x plus delta, right? So x is definitely less than c. So the limit as x approaches c from the left, that's a left-handed limit of f of x equals L, if this definition holds. Now we're not going to do a lot with these definitions. It's just I wanted you to see the formal definition so you know what the difference in these symbols is if I approach from the right or if I approach from the left. Now, a limit exists if and only if the directional limits agree. The limit exists if and only if the directional limits agree. And that's it. The function itself does not have to have a value there. So I can have a function that looks like this, with a hole in it like that. And if this is 3 and this is 2, the limit as x approaches 3 from the right of f of x, that equals 2. The limit as x approaches 3 from the left of f of x, that equals 2. The limit as x approaches 3 then of f of x equals 2. The directional limits agree. But f of 3 in this case is undefined. And that means f is discontinuous. Discontinuous at x equals 3. There's a hole in it. Okay, now let's look at this function. F of x is defined in pieces. And on your TA89, it's easy to enter these because you can just say y1 equals 4 minus x raised to the 2, and then put the big with bar down, x less than or equal to 1. Remember, you can use the diamond to get the less than or equal to. And put in y2 as 2 plus x raised to the 2 with x greater than 1. So that's how you can put the conditions on there and get your piecewise function down. Now let's see why this limit exists in both directions. Notice how it's done in pieces. On GeoGebra, I use the if idea. And you can put the conditions down. It's actually a little different in GeoGebra for those that want to do some of these for your homework. In GeoGebra, you have to go if, and then it puts the brackets down. Then you put down the function like 4 minus... first of all, you put down the condition, the condition, which in this case is x less than or equal to 1, comma, and then you put down the function 4 minus x squared. And then it's optional, you could just put down this. So if it's the complement of x less than or equal to 1, it'll do this one. So you can do an else part, if then else. Okay. Or you can just do an if-then for each of the different sections you have. But notice the difference here. The limit as x approaches 1 from the left, so let me color code this here. This limit is based on the idea that we're going to get closer and closer to 1 from numbers to the left of 1. So this is the limit as x approaches 1 from the left of 4 minus x squared. That equals 3. Notice I'm using the definition of f of x that uses x values less than 1. Now contrast that with this one. We approach 1 from the right. And the limit as x approaches 1 from the right of 2 plus x squared, that equals 3. So therefore, put those two ideas together and you get the limit as x approaches 1 of f of x equals 3. The directional limits agree, so the limit exists. Now let's look at a three-way defined function. It's a line, semicircle, and another line. And now let's look at these two directional limits. Oopsie, wrong way. So first here, the red section right there. Let's look at that red. X plus 5 with x less than or equal to 3. The limit as x approaches negative 3 from the left. As we get closer to negative 3 from points to the left of negative 3, that's this one. And that's getting closer and closer to 2. Now, as we approach negative 3 from the right, though, we're going to use this formula. So let me use green for that. There you go. The limit as x approaches negative 3 from points bigger than 3 is actually going down to 0. The limit as x goes to negative 3 of fx does not exist because the directional limits disagree. Okay? So we don't have a limit on that one. Now, though, if we look at the same graph, though, and look at the limit as x approaches 3. So let's approach it from this direction again. Let's take the purple this time. Now we're going to approach 3 from numbers to the left of 3, so it's like this. And that approaches 0. If we approach from the right, from numbers bigger than 3, it goes like this. That approaches 0 as well. The limit as x goes to 3 exists and is equal to 0 because the directional limits agree. The directional limits agree. So the limit as x goes to 3, in this case of f of x, equals 0. That's it. Flange out.